Great. So our third speaker is Nuraddin. He's going to talk about safe internal randomized path planning for manipulators.
Good afternoon, everyone. My name is Nuraddin Kerimov, and I am pleased to present our joint work with Aleksandr, Onegin, and Konstantin Yakovlev entitled Safe Interval Randomized Path Planning for Manipulators. While working in a sterile static environment is a pretty simple task and is successfully done by robots from 1980s, working in a dynamic environment is a bit of a challenge. And in our work, we focused on solving planning problems in the dynamic environment where the obstacle trajectories in the future are known. For example, they are predicted or are known in advance. For example, the obstacle is another robot with a fixed path. So let's define the motion planning problems that we are addressing. First, we consider an joint manipulator in a three-dimensional workspace. Then we define configuration space, which is a space of manipulator joint angles. And then we introduce a bounded time dimension with maximum time T max. Let's introduce obstacles. We have obstacles which position in space-time are known, including the future ones. The planners that solve this kind of problems are called deliberative planners. Now let's formulate the problem. We are given start configuration, goal configuration, and obstacle position in space and time. And we need to find such collision-free path from the start to goal, so the arrival time will be less than the maximum bounded time Tmax. To approach this problem, we use two main ideas. First one is a sampling-based search, like in RRT Connect, that's used to search in high-dimensional space of manipulator configuration space. And second one is we use safe interval reasoning for dynamic playing, like in SIP. So a safe interval is a time period for a fixed configuration where robot can safely wait without any collisions with obstacles. So let's introduce our planner. We called it safe interval RRT or SI RRT. And as RRT Connect, we use bidirectional approach, growing two trees, one from the start point and another from the goal point. And as a SIP, we use safe intervals and wait and go actions. And each node in SIRT is defined by its configuration queue and its safe interval. And also each node has a continuous arrival time to its safe interval. So start tree grows up in the time dimension and tries to arrive to nodes as early as possible, as in classical SIP. But goal tree grows down in time and tries to reach next node as late as possible, also to ensure reachability of the next node. So let's now define our algorithm. First, like in RT Connect, we sample configuration space and find new configuration by extending from the nearest neighbor by some limited distance. Slides aren't changing. Oh, now they're changing. Then we are finding getting safe intervals for this new configuration, and then we are trying to connect each safe interval to some parents in some radius, and we choose such parents that give us earliest arrival time to this safe interval. And then, as an RT Connect, we try to connect another tree to the new nodes. If we didn't reach new node, we just go to the step 1 and swap trees and doing everything for the goal tree. And we consider tree connected if they have same nodes with same configuration, same safe interval, and the goal tree arrival time is higher than the start tree arrival time. Because we in the goal tree we reach the next node as late as possible, now we need to trim those wait actions in order to get the best arrival time. So this algorithm is highly dependent on a safe interval retrieval function, and we now propose a method of fast computation of safe intervals. First, let's discuss how collision check is done usually. It's done in 2 steps. First step is broad-face collision checking, where candidates for collision are fastly computed. And then the narrow-face collision detection, where we exactly do the collision detection between these estimated pairs. So the naive approach to get the safe intervals is just to do the collision checking for each time step. And it can be computational inefficient if we have, for example, 1,000 time steps. So our proposed method is to combine all obstacles from all time steps into one scene, and keeping time steps from which we took the obstacles. In this slide, it's shown like a color of the obstacle, and when we do collision check once at this combined scene, we can get at which time the collision occurred. And because in broad-face collision checks complexity is logarithmic, it's also speed up retrieval of safe interval up to 200 times. So let's talk about our experiments. In our experiments, we use manipulating robot arm XARM6, and start and goal positions are fixed and the same for all tests and shown in the slide. As obstacles, we use small spheres that bounce around the 2x2x2 workspace, and we ensure that the start and goal positions are safe all the time. We vary a number of obstacles from 1 to 300 by 20 obstacle step, and for each obstacle count, we have 50 unique tests. We compare our planner with another deliberative state-of-the-art planner, space-time RT star, which is basically RT Connect star for space-time dimension with some optimizations. And this planner is anytime planner, and it can work in unbounded time. And also to validate our tests, we use state-of-the-art reactive planner from Manipulators, dynamic rapidly exploring generalized Bohr tree. We set time limit for 20 seconds. We set planner runtime limit also for 20 seconds for deliberative planners. And because all planners are sampling based, we repeat each test 10 times. Here you can see visualization of resulted paths for GRBT, SIRT, and STRT star. Note how SIRT waits in intermediate states. Here is experiment results. Now you can see a graph of success rate based on the number of obstacles. First, you can see that when number of obstacles is 120, the GBT success rate is nearly 0, while deliberative planners have 100 success rate. Also, you can see that SIRT outperforms STRT star on the high number of obstacles. Then we plotted arrival times and algorithmic runtimes for deliberative planners in the number of obstacles where their success rate is 100%. As you can clearly see, arrival times of SIRT is much lower, also as its algorithmic runtime. We thinking that our planner performs better because of the safe interval reasoning, and because it really can sense narrow space-time corridors. For example, here are safe intervals along the resulted path for SIRT on the left and STRT star on the right. And as you can see, SIRT did two weightings. First one is on the start position and in the middle, and arrived with low arrival time, while STRT star also solved this test, but with much higher arrival time. Also, we found the safety property of our algorithm. So because we know the time periods when it's safe to stay at the configuration, we can ignore really small time periods, and we can constrain the arrival and departure time from the safe interval, thus increasing real world application safety. So in conclusion, we proposed new deliberative planner, SIRT, and showed that it surpasses nearest state-of-the-art method in success rate, arrival time, and algorithmic runtime. And in our future work, we will investigate the theoretical properties of our planner. We will develop any time variants, and we will find new ways to get safe intervals fast and how to connect nodes. Thank you. That's all. I'm ready to answer your questions.
Thanks a lot. We have plenty of time for questions. Someone? Okay, so let me start. I was curious in the final part of your presentation when you were sort of avoiding the too narrow, let's say, safe interval. So when there is not enough time to stay there, you essentially prune, right? So does this, maintain the theoretical properties like of probabilistic convergence, or are you losing any completeness there?
We are definitely losing completeness because for the completeness we need to ensure the maximum reachability set, and by yes, we are losing completeness, but we are gaining safety. Because there are tolerances, there are noises in perception, and etc.
Clear. Do we have other questions? Still have plenty of time. There we go. I will bring you a mic, hoping that it works.
Thanks for the presentation. Okay, no, it's working. The work is very interesting. I was wondering how to deploy these in a more realistic situation in which, for instance, the obstacles or other the presence of other elements, or for instance, the presence of a user that is working around the robot. So how to extend your work in order to be applied in a more realistic scenario when you may have more difficult applications.
First of all, we tested our planner in multi-agent prioritized planning. So when other robots with higher priorities are treated like dynamic obstacles, and it worked very well and better than STRT star. And we also it's one of our future work on using classical observers from the control theory, machine learning solutions to predict obstacle trajectories in some time horizon in order to predict the path. And also there is plenty of machine learning solutions, for example, to predict humans' motion in future that can help us to deploy this in real world.
In case of robots, you know the dynamics in advance. You can foresee the trajectories and then the movements of the robots. of the humans, apart using machine learning, you may use just a probabilistic approach to compute sort of a convex area in which the human is moving, and then make another probabilistic approach managing the most probable presence or movement of the human, while interacting with the robot and environment.
Yes, of course. Thank you.
So I have two questions. One is, I assume your goal is to plan the motion for robotics arms, right? So is there a specific reason you modeled this problem as like single agent and treat all other agents as dynamic optical rather than like tandem joint space?
Single agent, and because it's very hard to represent obstacles in joint space. Or can you?
So my question is like, you have all the control. I assume you will have all the control on all each robotics arms. So why hand them one by one individually and treat all other arms as optical instead of just planning them cooperatively together?
Because each arm has 6 degrees of freedom. If we scale up it for 8 arms, it becomes like 6 by 8, 48, and it becomes very hard problem, 48 degrees of freedom. And that's why we plan them one by one in prioritized manner to have better scalability.
Yeah, I see. And another question is, why are you running bidirectional A star on the SIP instead of just single direction from start?
We run bidirectional RRT connect, not A star, and the reason is because one direction didn't work. Like we tried one direction, it didn't work, and then we tried bidirectional, and it worked.
Why it didn't work? Is it because like your branching factor is large and it just got lost in the search?
We think because so in the here you can see safe intervals along the resulted path, and we think that by using bidirectional search, we can shoot through these narrow space-time corridors, like very precise. Because when we shoot from the one-directional search, we can miss this tunnel.
Thank you.
Thanks. Do we still have questions? I have a curiosity actually. Do you think this is, could be useful in a task and motion planning kind of setting? Would it make sense?
Actually, we think yes, because if we find some way to project another robots into the safe interval joint space, and
My opinion, connecting with task planning, you can explore task planning to reduce the uncertainty and then be more effective in making assumptions about which are the intervals, for example, or in general, leverage the fact that you are also designing the task to better coordinate the movement.
yeah, something like that.
Okay. Cool. So let's thank the speaker again.